Dear viewers, having learnt about advanced concepts of thermodynamics, we are going to discuss about the fundamentals of chemical thermodynamics in this lecture. Many of my students have requested to revise the fundamental concepts. Hence, I am talking about the fundamentals of the chemical thermodynamics. I will teach you some of the basic concepts of the chemical thermodynamics in this lecture. Now, actually, the crux of the issue is that our experience, actual experience in converting one form of energy into another is summarized in the chemical thermodynamics. Conversion of one form of energy into another form. That is chemical thermodynamics. And from this, we are going to get information about the spontaneity of a reaction, whether a reaction can take place or not, or about the equilibrium. What is the condition for spontaneity and what is the condition for equilibrium? These are summarized in the first and second law of thermodynamics. You have two more laws, namely the third law of thermodynamics as well as the 0th law of thermodynamics. These two are not as widely used as the first and second law of thermodynamics. Before talking about this, let me tell you about some basic concepts. What is meant by energy? What is meant by heat? And what is meant by work? The unit of all the three are joules. Let me explain this also. Energy is a property of the system which can be converted into work or it can be obtained from work. Heat is a form of energy which is in transit. You don't say a body contains heat. We will only say a body contains energy. When the energy is transferred from one body to another body, that energy in transit is called heat and the unit is joule. What is meant by work? How do you calculate and what is the unit of this? All these things let us learn. I think it will be useful for the undergraduate students also. Work is nothing but, you are all aware of this, force into displacement is called work. What is the unit of force? In SI unit for force is Newton. In the CGS system, it is dyne. Let me discuss both the things. And displacement in terms of meter. So Newton into meter is called a joule. So the unit of energy, heat, work, all the three are only joule. What is force? The basic definition, you are all very familiar, you might have studied at the school level itself, is force is equal to mass into acceleration, F equal to ma. Mass is expressed in SI unit in terms of kilograms. Acceleration in terms of meter per second square. So this is called a Newton. Kilogram meter per second square is Newton. And work is, just now I told you, it is force into displacement. It is Newton into meter. Newton is kilogram meter per second square. This is meter. So a joule is nothing but kilogram meter square per second square. This is called a joule. Let me describe this in CGS system also. In CGS system, force is expressed in terms of dyne, mass in gram. Acceleration is centimeter per second square. So gram, centimeter, second minus 2 is a dyne. And work is force into displacement. Force is gram, centimeter per second square. Displacement is centimeter. So gram, centimeter square, second inverse 2. This is work. And this is known as what is called an erg. So joule is kilogram meter square second minus 2, and erg is gram centimeter square second minus 2. So let me relate these two things now. Namely, joule is equal to kilogram meter square second minus 2, and erg is nothing but gram centimeter square second minus 2. Let us find out the relation between these two things. How many x make a joule? A kilogram is 10 power 3 grams. And the relation between meter square and centimeter square is 10 power 4 centimeter square is a meter square into second minus 2. So a joule equal to 10 power 7 gram centimeter square second minus 2. And this is nothing but an erg. So 1 joule equal to 10 power 7 ergs. This is the relation between the CGS and the SI system. Then let us also learn what is meant by extensive and intensive property and exact differential. These are some of the terms which you come across in the thermodynamics. What is meant by an extensive property and what is meant by an intensive property? An extensive property is one which depends upon the quantity of the substance. And an intensive property does not depend upon the quantity of the substance. Say for example, mass is an extensive property. If you take more quantity, mass also will be large. For intensive property, I can say temperature is an intensive property. Irrespective of the quantity of the substance, the temperature will be same. So a number of such properties you can decide yourself, which is extensive and which is intensive. Then a note about what is meant by an exact differential or complete differential. Either you can call it complete differential or you can call it an exact differential. Let us say I have a property G, which is a function of x, y and z. Some property. G is a property which depends upon x, y, z. dg, the change in G equal to dou G by dou x yz into dx plus dou G by dou y xz into dy plus dou G by dou z xy into dz. The meaning of this term is very fundamental. Anyhow, let me explain that also. Keeping y and z as constant, change x by 1 unit. What is the change in G? That is dou G by dou x. And how many units you have changed? That is dx. To give a crude example, I would say that, say your weight depends upon how much of carbohydrate you take, how much of fat you take. Okay. So suppose you have taken 20 grams of fat and 20 grams of carbohydrate. What will be the change in the weight? All that you have to do is keep the intake of carbohydrates as constant, take 1 gram of the fat, find out how much of your weight increases. Multiply this by how many grams you have taken. Now next what you do is keep the carbohydrate as constant, change the fat. So this quantity tells you only this. Suppose they say G is weight and X is carbohydrate. For 1 gram of carbohydrate, what is the change in weight? How many grams of carbohydrate you have taken? If you assume that Y is fat, for 1 gram of the fat, how much of your weight increases into how many grams of fat you have taken? It's a very crude example. I think you will understand it. Okay, then the dg is called an exact differential or a complete differential. Okay, now what does the first law of thermodynamics tell us? The first law tells that energy can neither be created nor be destroyed. Energy can neither be created nor be destroyed. You can convert one form of energy into another form. You can't destroy energy. This is our experience in nature. That has been summarized as the first law of thermodynamics. First law of thermodynamics. I can even say that the perpetual motion of the first kind is impossible. You can't create any energy. You can't destroy any energy. You can only convert one form of energy into another. That's information given by the first law of thermodynamics. Mathematically, I can say like this. Suppose I supply heat to a system. Let us say the quantity of heat supplied is Q. A part of it is converted into work. Just now we told that it can't be destroyed. So the remaining would have increased the internal energy. I call it as dE. Q is the heat supplied, W is the work done, and dE is the change in internal energy. Suppose I have supplied 1000 joules of heat. The work done by the system is only 800 joule. The remaining 200 cannot disappear. It would have increased the internal energy of the system. So there should be energy equivalence. That's the information given by the first law of thermodynamics. How to calculate these quantities, W, dE, etc. Let us look into that. If a process takes place in a single step, the work done is given by the equation PdV. If it takes place in a number of steps, then W is given as integral PdV. You have to sum up everything. You have to sum up everything. This is for a single step process. I call it as an irreversible process. And this is a reversible process. Okay. What is the unit of pressure? Pressure is expressed in terms of pascals. Pascal is nothing but Newton per meter square. Pressure is nothing but force by area. These are some fundamental definitions. Force by area. Force is Newton, area is meter square. So, unit of pressure is Newton per meter square. This is what is called a Pascal. And volume expressed in terms of meter cube. So, this is Newton into meter, which is nothing but joule. This is how you calculate. If it takes place in a number of steps, slow steps, then in each step I calculate PdV and I add them up together. Integration is nothing but adding them up. So W is equal to integral PdV from a volume of V1 to V2. You know that according to the equation, gas equation, PV equal to nRT. So I can say it is nRT by V into dV from V1 to V2. If the temperature remains constant, a process wherein the temperature remains constant is called an isothermal process. So if the process is isothermal, N is a constant I can take out of the integration, R is gas constant I can take out of integration, and I said isothermal, so temperature is also constant, take it out, it is dV by V, V1 to V2. In other words, it is nRT, Ln, V2 by V1. This is how you calculate. This is how you calculate the work done in a reversible process. Since the temperature is constant, I can definitely replace V2 by V1 by P1 by P2, or W equal to nRT Ln P1 by P2. Okay, this is also very familiar to you. So this is how you calculate the work done. Then, before proceeding further, let me tell you what is meant by an equation of state. The four observable properties of a system is composition, pressure, volume, and temperature. These are the four observable properties of any system. The relation between these is called an equation of state. It is called an equation of state. The relation between them is called an equation of state. Let me write one equation of state. V equal to RT is an equation of state. This is for 1 mole. This is for 1 mole. Or PV equal to nRT for n moles. This equation is called an ideal gas equation. Van der Waals equation is also an equation of state. The Van der Waals equation says that P plus A by V square into V minus B is equal to RT. This is for 1 mole. And P plus M square A by V square V minus NB equal to nRT. This is for n moles of the gas. So this is also an equation of state. Well, let me just look into the informations of the ideal gas equation. PV equal to RT, I said. Or R equal to, what is the value of R? You can calculate. R equal to PV by T. Let me substitute the unit. Pressure is Pascal. I said it is Newton per meter square. V is meter cube. T is Kelvin. For 1 mole, per mole, no doubt about that, for 1 mole. That is equal to Newton into meter per Kelvin per mole. Newton into meter is nothing but joule. It is joule per Kelvin per mole. This is the unit of R. Let us calculate what is the value of R. Imagine I have 1 mole of a gas. 1 mole of a gas at standard temperature and pressure. Standard temperature is 273.14 Kelvin. Standard pressure is 1 atmosphere, which is nothing but 1.013 into 10 power 5 Newton per meter square or pascals. So using these values, let us calculate what will be the value of R. So I said that R equal to PV by T, R equal to PV by T. I have taken 1 mole of a gas at standard temperature and pressure. So 1 atmosphere pressure in terms of Pascal is 1.013 10 power 5 Newton per meter square. What is the volume? 22. 1 mole of a gas has a volume of 22.4 liters at STP. I want in terms of meter cubes. A liter is nothing but 10 centimeter into 10 centimeter into 10 centimeter. This is called a liter. Totally 1000 cc you say. In terms of meter cube, if I write 10 centimeter makes a meter. Therefore 1 centimeter is equal to 10 power minus 2 meters. So this is equal to 10 into 10 power minus 2, 10 into 10 power minus 2, 10 into 10 power minus 2, or 10 power minus 3 meter cube. 1 liter equal to 10 power minus 3 meter cube. So I can substitute here. Pressure I have substituted. Volume, it is 22.4 into 10 power minus 3 meter cube. Temperature 273.14 Kelvin. So this will work out to 8.314 joule per Kelvin per mole. This is a value of R. This is how you calculate the value of R. Instead, if I want to substitute the pressure in atmosphere itself. Volume in liters. Temperature in Kelvin. So it will be liter atmosphere per Kelvin per mole will be the unit of R. And if you substitute the values, it is 1 atmosphere, 22.4 liter, and 273.14 Kelvin. This will work out to 0.08205. So R can be substituted. If you substitute in terms of liter, atmosphere, etc., the value of R is 0.08205 liter atmosphere per Kelvin per mole is the value. Instead of liter, if you substitute in cc's, it will be 82.05 cc atmosphere per Kelvin per mole. So depending upon in which unit you submit, you have to substitute the appropriate R value for calculations. Okay, I was telling you about the first of thermodynamics, which is Q equal to dE plus PD. If the process is a constant volume process, let me denote it as QV. That is equal to just dE. Since the volume is constant, dV equal to 0, so PdV is 0. So QV equal to dE. And what will be QP? dE is E2 minus E1. E2 is the energy in the final state, E1 is the energy in the initial state, plus it is a constant pressure process, so P into V2 minus V1, final volume minus initial volume. I can rearrange this equation in this way: E2 plus PV2 plus E1 PV1. The quantity E plus PV is defined as H, enthalpy. It is defined as enthalpy. So this is equal to H2 minus H1, or this is equal to TH. So QV equal to dE and QP equal to dH. At this juncture, let me tell you what is meant by heat capacities. Heat capacity, the symbol is C. It is the energy required to increase the temperature by 1 degree. Suppose I do it at a constant volume. I will write like this. Energy required to increase the temperature by 1 degree at constant volume. I call it CV. Enthalpy required to increase the temperature by 1 degree at constant pressure, this is called Cp. So from this I can even write dE equal to Cv into dt and dH equal to Cp into dt. These are some of the basic things which you have to remember. These things come only in your undergraduate syllabus or even in your plus 2 syllabus. Only with this basic knowledge you can build up. Therefore I am teaching. A number of the students have requested that. Okay, so dE equal to Cv dt, dH equal to Cp dt. Cv is the heat capacity, that is the energy required to raise the temperature by 1 degree at constant volume. Cp is the heat capacity, same thing, enthalpy required to raise the temperature by 1 degree at constant pressure.